This is CSE 455 Software Engineering. We are meeting today, Monday, the 4th of May, which is the fifth week of our class. So hope everybody is all right. And we're moving on to the next topic of our class. But before that, I'd like to talk about deadlines, and I could see some discussions about deadlines. And so let me talk about that here, where you find uh, uh, things that needs to be done. As you know, you have revised your SRS. I've given you comments on what to edit on your SRS, and I ask you to submit the revised SRS yesterday, the 3rd of May. So I will look at it and return it to you for my final review. I also said that the software quality assurance plan and the software project management plan are due also yesterday, the 3rd of May, and the SQAP is the software quality assurance plan that is written by the QA teams. So the QA teams for Monday and the QA team for Wednesday will write their SQAP for the teams that are belonging to the Monday group, and the QA team for Wednesday will write their software quality assurance plan for the Wednesday group. Okay. The SPMP is the responsibility of the management team, and the management team consists of the project managers and the assistant project manager of each team. And the SPMP is the plan of the team on how to accomplish the first iteration by the 7th week of this class, and also planning for the delivery of the second iteration of the project by finals day. So repeating, SQAP is the responsibility of the QA teams, and the SPMP is the responsibility of the management team for every development team, which consists of the project manager and the assistant project manager. So this next document is upcoming. It is the software architecture and design. The software architecture and design shows in a graphical manner the different parts of your software. What are the components? What are the modules? What are the packages consisting of your software project? We need a design to determine all the modules that are needed to be developed and then put together with other modules to form the complete system of your software project. That's going to be kind of a ongoing activity, because I'm giving you from the 11th to the 15th of May to accomplish that. So this is a document that is, the design is a document that you need to um, um, write or draw while you are developing your code. So it is kind of a cyclic process you design, and then you code, and then you find out that the design needs to be revised. You design again, and then continue coding. So it is a kind of a cyclic um, um, process between coding and designing. And this is for the week of the 11th to the 15th of May. By the end of that particular week or earlier, between the 11 and 15, the software architecture and design should be submitted to me. Now, the software architecture and design is the responsibility of the management team again, the project manager and assistant project manager. Now, the detailed design, which is the refinement of the software architecture and design, will be the responsibility of the software engineers. So the project manager and assistant project manager will give the high-level design of the project, and then the software engineers will detail this high-level design. Now, for the delivery of the first iteration will occur on the week of the 18th to the 22nd. And during that week, the QA will be waiting for the teams to tell them that the first iteration is ready. And when they say they are ready, the QA team will take over your repository, and they will start the extraction from your repository, all the documents that you have in your repository. They will compile and build the mobile app execution module from your source code, and then they will install those compiled and executable code to the mobile device that they will use to test. Okay, so in other words, you will not hand to them a running mobile app on a phone, and there they will conduct the test. No, the QA team will extract from your repository the source code, and with your instructions on compiling and then building the mobile app, the QA team will have to do that. Okay, and so when they are successful in building the executable modules, they will run it on the mobile device, either Android or Apple device, the build the executable module, and there they will conduct the test. Okay, I will conduct, or I will again talk to you more about how the QA team will test your iteration. Okay, let's begin the software design here in a simple chapter that, or simple example that I have here. Okay, so let's say we have a software that would be installed to control elevators in a building. Okay, so there are n elevators in a building with n floors. So example is Jack Brown Hall. Jack Brown Hall has 3 elevators and 5 floors. Okay, so the problem concerns the logic required to move elevators between floors according to the following constraint. Okay? So each elevator has M buttons, one for each floor. So inside the elevator, we have M buttons, one for each floor, and they illuminate when pressed and cause the elevator to visit the corresponding floor. Now, the illumination is cancelled when the corresponding floor is visited by the elevator. So that's one of the given M buttons located inside the elevator, one for each floor of the building. Now, each floor has two buttons, except for the first floor and the top floor. Of course, the first floor has only one button, which is going up, and the top floor has only one button, which is for going down. Okay, so these buttons illuminate when pressed, and the illumination is cancelled when an elevator visits the floor and then moves in the desired direction. When the elevator has no request, it remains at its current floor with its doors closed. Okay? All right, so that's the given that we are supposed to design the, um, the software that will control the elevator buttons and the floor buttons. Okay. So what's the first thing we need to do to start the design of the software? Okay. The first thing we should do is to draw the use case diagram. And the use case diagram is identifying the different functional requirements of the elevator control system and identifying the actors of the software, the user, who is the passenger wanting to use the elevator, and the system, which is an abstract entity that controls the elevator. So these are just the few of the use case diagram of the use cases that we are going to identify. First, you want to request an elevator, and that request for an elevator is accomplished by pressing the up or down floor buttons that you have in each floor. So when you press one of the button, you are requesting an elevator, right? Okay. Another thing that the user is or the actor would request from the software is to order an elevator to go up or down. Okay, and the request the elevator to go up or down is actually a floor that you want to go to. So inside the elevator, you press the button of the floor, and so if it is above you, it will go up, and if it is below you, it will go down. So order an elevator to go up or down to the floor you like to go, right? Another function of the elevator control system is to open or close the elevator door. The user can open or close the elevator door, and that is also buttons on the panel that shows you the opening or closing of the door. Okay. Now the system has two use cases. It the user can press the floor where you want to go to, but it is the elevator that the system that would move the elevator up or down. Okay, so if you press, you are on the first floor, you want to go to the third floor, you press the third floor, and that registers a request to the elevator to go to the third floor. And the system will be the one to direct the elevator to go to the third floor. The system can also open or close the door for you. If nobody is pressing that open or close the elevator door, the system will do it for you. Okay, so there are other buttons that are other use cases that are needed by this system, but these are I would say, the major functions that you will need for this example. Okay, so you identified the use cases here, and you have identified the actors, the user and the system. Okay, now in the design of the system, you have a scenario of what's happening when you are using the system. Just like if you remember the analysis we did for the field officer and the dispatcher, and the organizer or sponsoring a league owner who is organizing a tournament. If you remember those examples, we have a scenario of what's going on, of how the software is used. So this is a typical normal scenario of how the elevator is going to be used. So here you have a scenario where a user presses the up floor at floor 3 to request an elevator, and that means the user wants to go up to the 7th floor. Okay, so press the floor button at floor third floor, wishes to go to 7. Okay, so he presses the up floor button. The up floor button is turned on, illuminated, and at some time later, the elevator arrives at floor 3. It has already a passenger, user B, who has entered the elevator at another floor, floor 1, and has pressed the elevator button for floor 9. So inside the elevator, 9th floor was already lit, and the user B actually did that. Then the up floor button is turned off since the elevator arrived. Elevator automatically opens. The user who pressed the up floor button at floor 3 enters the elevator. User A presses the elevator button for floor 7. So here, the user A, upon entering, will press elevator button for floor 7, wants to go to 7. Of course, when the button for floor 7 is pressed, it will light up. The elevator doors close, whether the user press the door close or the elevator control system closes. Elevator travels to floor 7. When it arrives at floor 7, the elevator button 7 is turned off. Elevator doors open to allow user A to exit. There is a timer that allows the door to be open, to be kept open while user A exits. Then after that timer, elevator doors close and elevator proceeds to floor 9 with user B. So this is a typical normal use of the elevator, just like what we did to the field officer and the dispatcher. We have a scenario of the normal use of the field officer to report an incident. And so what happens between the field officer and the dispatcher is depicted in a scenario, and we use sequence diagram actually to depict that. And that's part of the analysis, that we make sure that the requirements are fully understood. Okay, so this scenario is important to actually analyze the system design. Okay, all right. So from this initial scenario and the use case diagram that we have over here, we attempt to come up with an initial design of the software controlling the elevator. Now, design is not done in one single step. It is also an iteration process, because what you do, you come up with the design, analyze it, and if you find it's inadequate, then you revise your design. And you keep doing this in several iterations until you're satisfied that the scenario will be fulfilled, okay, or will be accomplished by the software. So here is your first iteration of the class diagram that will be developed. So the class diagram consists of course, there are two kinds of button, and the elevator button and the floor button. Remember, the floor button is the up or down floor button of the building, and you have two buttons for every floor. M is the floor, 2m minus 2, because the top floor and the bottom floor, floor number 1, have only one button each. Okay, so it's 2m minus 1, and for the elevator button, there will be m buttons, one for every floor inside the elevator, and they communicate to the elevator. And the elevator, as you can see here, is a class, and it has a one member variable that is a boolean of the doors, and this is a boolean value of whether the doors are open or closed. Now the other classes, elevator button and floor button, are subclass of the button, and the button has as of now a single member variable called illuminated. It's a boolean value also, whether it is lighted or not lighted. And this symbol here is a inheritance, which has that depicts the relationship that the elevator button and the floor buttons are subclasses of the parent button, which is here, the class called button. Also, the elevator communicates with the elevator button. As you see here, there are m floors, and there are n elevators. So this is a many-to-many communication between the elevator and the elevator buttons. And for the floor buttons, it's for every button there is a 1 relationship 2m minus 2 to 1 elevator uh, um, um, uh, uh, association. Okay, so this is one to many, and this is many to many. Okay, so the initial observation here that this many to many is going to be a difficulty in the implementation of this software. So you have M buttons, elevator button, communicating with N elevators. That's kind of, if you're going to implement the system, it's um, going to be a rather a complex interaction between the elevator buttons and the N elevators. Okay, so we want to eliminate that many-to-many communication. So what we do is try to remove that many-to-many communication. So what do we do? Well, this is what we do. We separate the elevator into two classes. The elevator controller, which is just one, and the single controller is controlling an elevator. So that's how you remove the many-to-many communication. So there is a centralized controller that knows everything about where the elevators are, communicates with n elevators, and the elevator controller controls the M to N, M times N elevator button. So now all the floors and the floor button and elevator buttons are communicating with the elevator controller. And so this is how you um, um, go through your design, always looking for simplifying your design. So this is kind of easier to do because we have one elevator controller which is centralized, and all the information about the floors, floor button, elevator button, and elevator are all concentrated here on this elevator controller. So you might say, okay, I think this is a good design. Now notice here that the classes are not fully defined. That's okay. In the design, you can start with the name, just the name of the class, and one or two variables, member variables, and one or two um, member functions. That's okay. So you can fill it up as soon as you are, now that you know more about the the advantage of the advantage of your design. Okay. Now we are still not happy here because the doors, as you see here, is controlled by the elevator. Now doors are very important variable. Would you allow the doors to be controlled by the elevator right here? Or would you like the doors to be controlled by the elevator controller? Now, since we say the elevator controller controls everything, he should know everything about what's happening to the elevator, and the doors in particular are very important. Can you imagine pressing a request for an elevator and the doors open, but the elevator isn't there? So if it is early in the morning and you are still sleepy, you might step into an empty elevator, and you have a bad accident falling into a elevator shaft, which is not going to be nice. Okay, so we have a third iteration that shows the elevator controller controlling the elevator doors. Now, this is better because elevator controller knows where the elevator is, and therefore, when the elevator reaches a floor, it will open the door of the elevator, okay, and not the elevator controlling it. So this is kind of the completed design where two other classes were identified. There are elevator application that the elevator needs, like for instance the timer, which was mentioned um, uh, in the description of the software, and timer for opening, closing the door, other applications like emergency calls, if there is a need for emergency for the passengers to ask for help, and elevator utilities that the elevator might need. Like for instance, um, it could probably need a utility to make the elevator efficient in answering for a request. So if there is a closer elevator to the request, then that elevator should fulfill that request rather than a very far elevator to fulfill a particular request. And you want the movement of the elevators to be efficient, not to be moving so much that the elevator time is spent moving up and down the building to service a request. So you want the movement of the elevators to be efficient, the least amount of moving from floor to floor to answer a request. So the design is complete now, and you can actually build your software based on these classes. Okay. Now the last step is for the sequence diagram to be done so that you can actually analyze your design. Okay, make sure that you have covered all functions. Now this is based on the scenario that we have at the beginning. So user A begins by pressing the up button from the floor he was in, that he wants to go up. So who receives that pressing of the button? It's the elevator controller. Remember, elevator controller has the all the information. It's a centralized control. So when that button is pressed, it registers a request in the elevator controller, and elevator controller will now record that, hey, there is a passenger requesting for an elevator. So the what will happen is the first thing that the elevator controller must do is to turn the light on the floor button on. Okay, and sometimes some of you are so impatient waiting for the elevator that you want to that you press that button many times, and I've seen that for some users who are impatient and press the up floor many times, and you know, when you press it once, the request is already registered, so pressing it again won't hurry up the elevator to your floor. Okay, so it is kind of a human behavior to be impatient and kind of request again the elevator, thinking that his request was not registered. Okay, so next thing, elevator controller will command the elevator to move the floor, to move the elevator to the floor where the request was registered. Okay, then once the elevator arrives, so here, remember, sequence diagram, time is increasing as we go down. The elevator arrives at the user A who press a request for an elevator, so controller will turn that light off. Okay, and then at some time later, the elevator controller will command the elevator doors to open. So doors will open, and then this particular time here is the time for the user A to enter the elevator. The user will press elevator button 7. He wants to go to floor 7. Remember that? Okay. And so after pressing it some time, the elevator controller will tell the elevator button to turn on. Lights turn on. And then the timer will command the elevator controller for the doors to close. Here is the elevator doors to close. Okay, doors close. And then close the door, and then the elevator move to the floor, move up one floor. If there are any passengers there, they will pick it up and will continue if there is no request for that floor. And then once it arrives at the destination, 7th floor, it will turn the elevator button for 7 to off. At the end of some time, the door will open. So elevator controller will tell the doors, hey, open up. Okay? And it will start a timer. Elevator controller start a timer. And at the end of some time, it will tell the doors to close. And then command the elevator, hey, move up one floor. We are going to floor 9, where another user wants to go to. So it's a kind of analysis of the scenario if you are able to, if the design will fulfill the function that you requested. Okay? So very nice software process for design. Design, and at the same time testing your design if it will work. Okay? So the thing with design is that yes, you have a nice picture of the design, but will it work? How do you know this thing will work? Okay, you haven't written the code yet. So and that is why software architects are paid a large amount of money, because the design should implement the system, will be the guide by the coders to actually begin coding based on this design. Okay? All right, so the sequence diagram will help you analyze. All right, and here is a more detailed picture of the design. And so for the buttons, we have first a Boolean algebra, a Boolean variable for illuminate. And here are the two functions of the member functions of button: turn button off, turn button on. They are abstract definition here, but you define it here of what those functions really mean for the elevator button and for the floor buttons. Okay? And here we have doors open. It's a member variable, and closed doors, open doors are member functions of the elevator doors. And the elevator here has member functions: move one floor down or move one floor up. So elevator controller will tell the elevator, hey, you move up one floor or you move down one floor. An elevator will execute this function to move one floor up or one floor down. Okay? And now we call this detailed design. Okay? Now, detailed design of a method, elevator control loop. So this is a method or a member function in the elevator control loop that write the code, not yet in the source code, but in a pseudocode, algorithm like. Okay, so notice here that it is not a particular language like C or Java, but it's close to the structure of a programming language, except it is not following the syntax of that language. And here is the method called elevator control loop. This is a function that is in the elevator control system. And here is a do. So the scope of the elevator control loop is from here to here. Okay. And then the do loop scope is from here. That's the begin. And this is the end. So actually, what you see here is an infinite loop. This code will be called infinitely over and over again. Okay? And here is the if construct. If a button has been pressed and if the button is not on, then we call the function button turn on and log the request. Now notice here that some may look like C, but others are like a high-level language, like English-like. Okay, so at the algorithmic level or pseudocode, you are not worried about the syntax of the language you are using. C or Java, it doesn't matter, although it has braces and a semicolon, but that's the extent of the syntax. But you can use sentences like log request. So this means the request for for elevator is logged into the elevator controller, which controls all the elevators. Okay, and that's the end of this if statement. Here is the else. If the elevator is moving up, so the elevator is in motion, if there is no request to stop at floor whatever, elevator will move one floor up. So if it is on the way up, it will continue going up. And there is no request to stop at floor F. Else, that means somebody is requesting elevator at that floor, stop the elevator, okay, by not sending a message to move, okay? So stop the elevator, and this is where the doors are open, and if the elevator button is on, turn it off and update the request. So update request means remove the request from your queue and serve the next request. So that request has been served. So no need to um, no need to service it. Okay. Now here is another else here, that is if elevator is moving up. So here is the other else. This is kind of a case statement. If the elevator is moving down, it's on the way down, similar to the up case. Else, if so similar to the up case means copy the code for the up case. Okay, so you don't need to repeat that. And then after that, if if the elevator is stopped and request is pending, here is what you do. Elevator doors, close the doors. So if the elevator is not moving, it is stopped, and there is a request that is pending, the elevator will close the doors. And if the floor button is on, somebody press it on in the floor button, and the floor button then turn it off. Okay, if the floor button is on, turn it off. Determine the direction of the next request. Okay, so there is a request for an elevator. The elevator is stopped, and so it will go to that particular floor. Determine where the direction up or down. Elevator move up or down. And that's the end of when the elevator is stopped. And here is another case. If the elevator is at rest and no request is pending. Okay, so the previous one is stopped and request is pending. So this one is at rest and not there is not a request pending. Then it close the doors, and then else, if not, then the elevator is stopped at that floor and do nothing. So the advantage of doing this, the pseudocode and not yet the source code, is that you will be able to actually test the pseudocode for logic error. Okay, sometimes errors are caused by logic, and the logic could cause your program to fail. So doing it in pseudocode, excuse me, would allow you to actually determine the logic error before source code is done. It's easier to debug and fix problems on the pseudocode than to fix errors or bugs on the source code. Which one would you rather fix, pseudocode or source code? Okay, pseudocode is easier. All you need is pencil and paper. You erase and you rewrite. Okay, but the pseudocode will be easier to fix and test for logic if there is any problem. Okay, remember that. And that will be one of the testing that we will be testing technique that we will be using before the source code is written, which is testing the logic of the pseudocode that you have written. Okay, now as a last topic here for the simple example, you should also include abnormal scenario, and this is very important. if you only use normal scenario, an error could occur in an abnormal scenario. And if you didn't consider the abnormal scenario, and that happens when the software is already deployed, your software could crash, okay, or perform something unexpected, and you don't want that, okay? So in the design, in addition to normal scenario, you also include abnormal scenario, okay? This is important because abnormal scenario can happen, and if your software did not consider abnormal scenario, your program could crash. Okay, let's look at this. So here the user A presses the up floor button. It is at floor 3 to request the elevator. So that's he's at floor 3. He wants to go to floor 1. Okay. He wants to go up to floor 3. He's at floor 3 and he wants to go down. That's the error there because he pressed the up button. So the up floor is lit up. Up floor is lit up. No, I'm sorry. He is at floor 3 and he wants to go to floor 1, but he pressed the up floor. Okay. So the up floor button is turned on. Elevator arrives at 3. It contains a user that has entered at floor 1 and presses 9. So up floor is turned off. Elevator doors open. User A enters the elevator and user A press 1. Okay. Now the user pressing floor 1 when the up floor button was pressed should be handled by the elevator control system that there was an up floor request that is pressed, and yet this user presses floor button, elevator button for floor 1. So the system should be able to handle that difference of requests, okay? Because if you did not consider the this particular scenario that the up floor was pressed, then system could be confused because if it is not included in your use case, in your case statements in the algorithm, it's unpredictable what the system will do. Okay, so here in this scenario, what will the system do is ignore the up floor request and proceed to floor 1, even though the up floor request was pressed. Okay? All right. So let's proceed to the next topic. Okay. Let's move on to the next topic of our lesson today. And this is the system design, decomposing the system. Let me go to my figures. Okay. We have talked about design, and design is your blueprint of how to build your system. And here is an example, not for software, but for designing the floor plan of your house, for instance. And here you see 3 iterations of the design. And the first design looks like this. And you notice that the dining room is very far from the kitchen. Okay, so you don't want to bring food through the hallway and serve it in the dining room. So what we did was to exchange the dining room and the bedroom. And so the dining room is going to be here and the bedroom over here. Okay. And then you notice that in your second version, um, that the dining room could be uh, expanded and have a bigger um, area by removing the bath and inserting it here between the study and the bedroom. But of course, the bedroom too will decrease in area, but you occupy the hallway to compensate for that. So you are on the third version. And I think the third version isn't still done because if you notice, there is only one entrance. There's only one entrance, and there's no back door. So if there is a fire and the fire is blocking your entrance door, you'll all die in this particular design. So it's not a good idea for the bedroom to occupy the hallway. We should keep that hallway to provide for an exit in the back door. Okay, so that particular design has a fourth version. But what I am saying here is your design is never done. Your design keeps on being improved because you notice something that could be made better. So it's the same with software development. You have a software design, and sometime later, when you are coding, you notice a flaw in the design, and sometimes it cannot be avoided because there was incomplete information at that particular time. So you want to change it. But of course, you have to stop coding and fix your design. Once the design is fixed, you continue coding. And this is probably what's going to happen in your development. You will have a design, but then you will constantly fix it as you discover more and more about the issues in your software. And what if there's already an existing design? Okay, well, you have to continue that design since you are continuing the project, but later on, if you find some issues in the design, then you have to fix the design and um, uh, and edit the corresponding code for that. So it's a never-ending process. You always have something to do for maintenance. That's the software life cycle. Okay? All right. And you've seen this diagram about the initial part of the software life cycle where you have analysis, you determine the non-functional requirements, and you analyze the non-functional requirements and the functional requirements through a sequence diagram, and then you have your system design coming out of the analysis, and you identify design goals and subsystem decomposition. So the subsystem decomposition is the high-level design that I am talking about. You got to begin from some high-level design and then refine it to more detailed design at some time later. And the purpose of the system design is to determine high-level modules and components of your system, and yeah, you can't deal with the detail as of this time because of incomplete information. And then the final design is the object design, giving you the object design model. Okay? All right, so let's look at some high-level design. Now, high-level design is um, represented here in UML diagram called the class diagram, or it could be class diagram or the package diagram. Okay, so here is a subsystem decomposition of an accident management system. So remember the field officer and the dispatcher system that we use as an example. So the field officer interface is represented here by a class or a package diagram. I will call this more package diagram because we don't know the detail of the field officer interface. Remember, there are two interfaces, one for the field officer and the other for the dispatcher interface. There is a map management that the field officer and the dispatcher look at, so they are looking at the same map to determine the location of the incident. The dispatcher will produce an incident report, and dispatcher will also produce resource management, that is the sending of resources like ambulances, fire trucks, and even police for investigation, and a notification that the field officer's report was accepted. So here is the entire design, system design of that particular example of reporting emergency incidents. Okay, so you think of the entire reporting system as consisting of six different components. Okay, so that's the first thing you want to do in a design, is to determine the major components of your software. And here, for that specific problem of the reporting emergency system, we identified three high-level components of the system. Okay? All right. So, and in this database design for the emergency reporting system, there are two designs that was given: the incident management, the resource management, the map management, access a database. So this is one design of the of that software, where the all of these components, map management, resource management, and incident management, all access the database. So all of this map management, incident management, and resource management access a common database. Okay? But in the next design, instead of accessing the database directly, you have a storage, another package that is an intermediate component before you access the database. So all of these components, map management, resource management, incident management must go through the storage first before accessing the database. Now, there are advantages and disadvantages of this two design, okay? Here, in this design over here, um, this design is more secure because you have to go through storage before you access database. So storage can actually include um, some kind of a gateway before access to the database is done. And another advantage of this design, if I change the database structure, code, or anything, the other components, map management, resource management, incident management, doesn't need to know that because they are interfacing with storage and not database. So if you change database, all the changes that you have done to the database will not affect the other three components. That's the advantage of this design, okay? But the disadvantage is you put an extra component here before accessing the database, so efficiency could be affected. And the efficiency is you have to go to the storage before you go to the database. Whereas over here, the disadvantage of this design is if I make changes to the database, all the other modules or packages must know about that change and they could be changed as well. But the advantage of this design is efficiency. They can access the database very quickly. Okay, so those are the pros and cons of a specific design that that could affect your decision of which design will be better to use. Okay, so with that, I end the lecture for today, and we'll continue with systems design, decomposing a system, subsystem later on. And so I'd like to say be safe and be healthy. I'll see you next time.